Hello and welcome back to Making a Synthesizer in C. This is episode 4. So today we're going to have a look at band-limited waveforms. I mentioned in episode 3 that actually there's an issue with our waveforms, the non-sine wave ones, the sawtooth, the triangle and the square. And that issue is called aliasing. If you remember back to episode 1, I talked about the Nyquist theorem and the Nyquist limit. So at the moment our sample rate is 44,100. So that's how many samples per second our audio waveforms are. And so our the limit of the frequency of any one waveform is easy to calculate. It's just the sample rate divided by 2. So we can't have any frequencies higher than 22,050 Hertz. What happens if we do go over that is actually you end up with a lower frequency. It folds back over on itself. So for example, if we try to represent a frequency at 33,000, you're actually going to hear a lower frequency than 33,000. And that's called aliasing. So there was an excellent resource on the web that I found a few weeks ago, and unfortunately the website's gone down, the website's offline, but I did manage to take some screenshots of it on the Wayback Machine. So let's try to explain what I mean by all this. So, sampling a waveform, this is what we've been doing. A sine wave signal can be generated with the sine function, or we're using the sine f for float. By taking measurements of a sine at regular intervals, a discrete signal result, each measurement is called a sample. So this is what we've been doing. 44,100 times a second, we're sort of taking a snapshot of where the signal would be. Great. So, an ideal square wave is a simple oscillation between two amplitudes without any intermediate values. So we start at -1, and then we immediately jump up to +1, then we immediately jump down to -1. However, sampling an ideal square wave doesn't work well for most frequencies. So here's a sampled ideal square wave. Examination of the result reveals an obvious problem. Some cycles have an extra sample, and we can see this here. This one has 4 samples, this one has 4 samples, but then this has 3 samples, then 4 samples again. When played, it sounds muddy. The concepts of the Nyquist limit and harmonics will give better insight into the problem or point to a solution. So I can showcase this if we open Audacity again. So in this one we've got much lower. We've got 16,000 Hertz. This is project rate. That's our sampling rate. So let's go ahead and generate a square wave. Let's set the frequency something a little high, 700, and let's zoom in on this. So here's our square wave, and then here's our samples. In fact, I'm going to make the frequency even higher. Generate a tone, let's do 1200. So we can see here, these are the individual samples. This is our negative and our positive. You can see this has 1, 2, 3, 4, 5, 6, 7. And then this has 1, 2, 3, 4, 5, 6, and then 7, and then 7, and then 6. So we got the same problem. Now if we try and listen to this, it will be, I want playback speed at 1, it's the volume. Let's set the volume really low. So that's what it was saying, it's got a muddy sound. It's not quite sharp, which is what you would expect from a square wave. Yeah, so let's continue. Page 3, the Nyquist limit. So we've already talked about this. The simplest sound wave is an oscillation between two amplitudes. A sampled waveform first needs at least 2 sampled points per cycle. Right, and that kind of intuitively makes sense. You need at least 2 points per cycle, one to represent the peak and another to represent the trough. Any less than that, then we can't even have the most simplest triangle wave. Put another way, the wave's frequency must not be above half the sampling frequency. This limit is called the Nyquist limit of a given sampling frequency. So sine wave at half sampling rate with 2 samples per cycle. So I can explain this. So we got our sample rate at 16,000. So we're going to generate a tone, a sine wave. What's half of 16,000? It's 8,000. So let's see what happens if we try and generate. I think in our Audacity, if you go over 8,000, it doesn't even let you generate that tone because it knows the sample rate's 16,000. You can't have a frequency higher than half that. So if we do it at half, we just get nothing. We get a flat line because we've reached the limit. Absolute silence. And the reason for that is because it's going to be sampling. Basically, it just so happens every time it samples it, it's sampling it at this point where it lies on the 0 line. And that's all you get to see. If a sine wave higher than the Nyquist frequency is sampled, or if a sine wave higher than the Nyquist frequency is sampled, so if we go over 8,000, a sine wave of lower frequency results. This effect is called aliasing. So you can see here where it takes a sample that coincidentally creates this lower waveform. So one way we can do this is by generating a tone. Let's generate a tone at 5,000 Hertz. And we can analyze this. We can say, hey, plot me a frequency spectrum. So what this is doing is analyzing the waveform and figuring out what frequency it is. So if you look down here where it says peak, and I hover over this peak, it says 5,000 Hertz. That was the frequency we set when we generated the tone. Now what I'm going to do is I'm going to tell Audacity to resample this wave at half the sample rate, 8,000. Now listen, it's lower in pitch. All we've done is resample the waveform. And if we go to analyze it now, we can see the peak is exactly half of what it used to be, 2,500, because we've halved the sample rate. So this is aliasing. Since an alias is no different than a normally sampled wave of the same frequency, aliasing can be avoided only by removing frequencies above the Nyquist limit before sampling. So to prevent this aliasing effect, we need to modify how we actually generate our waveforms. So, square wave harmonics. A square wave can be constructed from multiple sine waves at different frequencies. The sine waves added in addition to the fundamental frequency are called harmonics. A square wave has harmonics at odd multiples of the fundamental frequency. As higher harmonics are added, the result gets closer to an ideal square wave, which contains infinite harmonics. So basically what this is saying is we can make shapes like square waves and saw waves just by summing up various sine wave shapes. And we actually did that accidentally in the first episode. We managed to make a sawtooth looking wave just by summing up different sine waves. Let's try and do this properly. So it's got the function here, look, sine angle. This is basically our sine phase. And then we had another one, but it's 3 times divided by 3. So this divide by 3 here is basically our amplitude. I notice it's doing a fundamental plus odd. So we could do this. Let's have a look. Let's go down to where we're setting our oscillator amplitudes. And for now, we're going to set the triangle, square, and sawtooth to 0. So actually we want, if it's the fundamental, so the fundamental is the first or odd, so that's does not equal 0. we're going to set this sine wave to that amplitude. Otherwise, we're going to back to this view, set it to 0. So the fundamental frequency, which is going to be our first oscillator, and all the odd numbered oscillators are going to have this amplitude in decreasing order. And then if we come to our handle audio stream, we've got our base frequency. For now, I'm just going to comment this out and just say our base frequency is equal to 500 Hertz. These aren't going to get, I mean, we're updating the other shapes, but we've set their amplitudes to 0, so they don't matter. And then in our update oscillator array, we actually want the frequency to be the frequency times I plus 1, because we're counting I from 0. So we want the fundamental to at least be not multiplied by 0. We want it to be multiplied by 1. Let's give this a go. So it was build and run. Do we have enough oscillators? Let's bump this up to 32. Maybe not, maybe just 16. So not working quite how I expected. Synth, sine wave. Our LFO should be set to 0. Yeah, let's get rid of the LFO for now because that might be alright. Let's lower the base frequency a little bit to 100, just so it's a bit. So this looks more like a saw wave. Make sure this amplitude's correct. I'm going to printf the various amplitudes. So we got sine number 1, or sine fundamental amp. It's going to be sine osc 0, the amplitude. Oh yes, I see. Because the fundamental is 0. Again, it's a whole issue of counting from 0. Means that our odd numbered oscillators are actually going to have an even index. So we actually want to say equals equals. So this will say is the index even. I don't think we need to do this. Let's have a look. There we go. You can see we're now making somewhat of a square wave. So if I bump up the frequency, let's go twice as high. And let's increase the number of oscillators. So if we did 20 oscillators, you'll notice it starts to converge closer and closer. still have a feeling our amplitudes aren't correct. So 1, 2. So this is fundamental. This would be the third one. 4 would be fifth one. 6 would be the seventh one. Let's just print that out. So 3 should be reciprocal. Should be 1 divided by 3, not 0.933. So our amplitude logic is incorrect. What it should be is pretty simple. It's just 1 divided by I plus 1. There we go, that's what we were looking for. And then you can see that here. So the third oscillator, we're dividing it by 3. Fifth oscillator, we're dividing it by 5. The seventh oscillator, we're dividing it by 7. So if we only did 6, we'd get, if it was just 2 oscillators. So you can see how it starts to get closer and closer to sine wave. 8. I mean, closer and closer to a square wave. 16 stacked on top of each other. Let's do 32. Let's do 64. I'm doubling these numbers each time. Let's do 128. This is how it gets closer and closer. Let's stick to 16. That was a close approximation. Let me increase the volume ever so slightly, because it is pretty quiet. One. So the problem we've got here now is we're going up to 16. So the highest frequency is going to be our base frequency, which we set to, where did we set our base frequency? 200. So let's consider the worst case, where I equals 15. So we've got 200 times 15 plus 1, that's 16. Let's do that as a calculator. So 200 times 16, 3,200. So that's fine, that's way below the 22,000 range. But what if we have a higher base frequency, such as 1200? Well, now this is going to be 1200 times 16. So we're going to have 1200 times 16. Still squeaks under the 22,000 range. So let's do 1800. So 1800 times 16. Now it goes over 22,000. That's above our Nyquist limit. So let's give that a try. Another way we could do this is, instead of making our base frequency higher. Say, let me put this back down. Let's go 500, but decrease our sample rate to 8,000. Or even lower, 4,000. See how that. So 2,000. It should be going lower and lower in pitch. Let's put it back to 45,100. And then let's bring back our interaction. I'm going to go from plus or minus 800. What we can do here is we can say if the oscillate frequency is lower than the sample rate divided by 2, then we'll update it. Or probably a simpler way to do this is if it's greater than or equal to, we'll just continue. So continue basically tells it skip everything in this block from this point onwards and just jump back up to the loop and start on the next incremented I value. So I'm going to go back to our sample rate, set this to 8,000, maybe increase this to, I don't know, 24. Let me decrease this even more. And then if we didn't have this block, what would it sound like? There we go. So it should be really obvious. Let me make this louder. 6.1. So this prevents aliasing, because if the frequency goes over half the sample rate, we would continue. But I've commented this out. So as I get higher in frequency, notice it sounds, you get all these other weird frequencies mixed in. But it's alright at the lower. So I'm going to uncomment this so it prevents aliasing. It's a subtle difference, but it's definitely there. Again, comment this out. Now we have aliasing. Especially at the very high end. Without aliasing. It's really obvious at the higher end. So that's all well and good. Let me put our sample rate back to 44,100. But creating shapes this way by summing up a whole bunch of sine waves is not very efficient. So let's come back to this. Okay, page 5. Band limited synthesis. A band limited waveform is one whose harmonics are kept below a particular frequency. If a waveform is band limited to the Nyquist frequency and then sampled, no aliasing will occur. That's what we've just done with the additive synthesis method. Below are two sampled band limited square waves. Even though many of the ripples seem to be unrepresented at the sample points, none of the signal is lost since there are no harmonics above the Nyquist frequency. And you can see that this shape is the shape we were getting. Page 6, band limited step. Generating a band limited square waves by adding sine wave harmonics take a lot of computation, as we've seen. Examining band limited square waves reveals a similarity which allows a simpler method of synthesis. The Ripley shape at the edges of the transition stays the same regardless of the frequency. So you noticed when we would do that, we would get this big ripple at the start of the transition, and then it would sort of decrease in rippliness during the positive or negative section, and then as it transition again, we get like, woo. An ideal square wave has a step at each transition between amplitudes. Likewise, a band-limited square wave has a band-limited step at each transition, since the ripples around the transition quickly fade away in either direction. A band-limited step can be practically generated by synthesizing a low-frequency, band-limited square wave and cutting off the ends. The result, adjusted to start at 0 and end at 1, is a very useful band-limited step. Using a band-limited step, a square wave of any frequency can be synthesized by adding steps of alternating sine at regular time intervals. Here, two band-limited steps are sampled and added together to form one cycle of a band-limited square wave. So let's have a look at how we can do this. Effectively, we're going to be stitching on these ripples on either side of the transition of a square wave. So if I come to my resources text file, there was another blog post that described this pretty well. So let me bring this here. And let's have a look at this. So I'm just going to come down. This talks about a lot of the same things we've just been looking at. So here it goes. It's called a PolyBLEP oscillator, BL for band limited. So I believe this is the math we want. PolyBLEP takes in T, which I believe is our phase. Remember, we have our phase incrementer. So we're going to pass in that. Delta T phase increment divided by 2 pi. So if T, so let's see how this would map to our code. Where we have our update oscillator function, here's our phase. We update our phase, so this is our phase delta. This is our phase and this is our phase delta. Let me come back to this. So this is dt, this is dt. So if t is less than dt, basically this is a bunch of maths to create that ripple effect. We just have to trust that it works, I think. The math may look complicated, but basically this function always returns 0 except when we're close to an edge. The first if branch means we're at the beginning of a period, and the else if branch means that we're right before the end. This is the right behavior for a saw wave, because in a saw wave there's only one jump, which is between two periods. Yep. So here they're using a switch statement for calculating the various shapes, whereas we're using different arrays. So when you get in the next sample, yep, they're doing what we're doing. Phase plus equals m phase increment. Again, that's this line here. When phase is greater than 2 pi, so that their phase is, I'm guessing, between 0 and 2 times pi, whereas we've normalized it between 0 and 1. So we might have to account for that. So the sine stays the same, oscillator mode sine, but for things like saw, they calculate the saw and then they add this PolyBLEP to the sample. And then for the square wave, they have to do PolyBLEP twice, one for the start and one for the beginning, I'm guessing. All right, let's give this a go. So the function question is this we need. I'm going to put this up here. We're using float. So we're going to do PolyBLEP. We're going to call this a band limited ripple. It's going to take in a float. That's going to be our phase. We're going to pass in our phase dt, yeah. So we don't need to pass in, we don't need to calculate that. So if our phase is less than our phase delta, then phase equals phase divided by the delta, and then I'm going to return phase plus phase, t phase delta, phase equals phase delta. Otherwise, return 0. These need to be floats. That's why I put f on the end. Float. All right. So let's come back to this. So we probably will need to store the delta. So we're putting back, I think we took this out in a previous episode. Now we're going to put it back in because we do need to reuse this. So we're just going to say os.phase dt equals this line here. And then it's just os.phase dt. Pretty simple. And now we need to put this into the shape. So I'm going to say float sample equals this. Let's come back to this. Look, we minus equal. So we do sample equals sample minus band limited ripple, oscillate phase dt. And then for a sample wave, again we say float sample equals that. And how did they do it for? We did plus equals and then minus equals. Is this f mod? After half a period, the square wave jumps to all -1, so something of those means a linear decay. This time though, we're adding 2 PolyBLEPs, yep, one at the start of the period and the other offset by 0.5. Which is why they're doing modulo, so if you offset it 0.5, it'll wrap around, and you're already above 0.5, it's going to wrap around back to 0. Yep. I get it. So we do sample plus equals band limited ripple, oscillate phase, oscillator phase dt, and then we need to do sample negative equals band limited ripple, f mod, os phase plus 0.5. 1.0 and then os phase dt. We need to return the sample. Alright, what about triangle? So how come they don't use it here? I guess because there's no instantaneous, the only instantaneous bit in a triangle wave is when it reaches the peak. There's a bit of like an instantaneous deacceleration to go negative again. So they've just got a, I mean, we could just copy this code for our triangle wave. But it does mean we need we'd have to add an extra, got this last output here. We'd have to add an extra float to our oscillator class. So I'm not going to do this for now. I'm going to do make this band limited C code below. Requires adding extra field to oscillator. So I'm just going to make a comment. Okay. Yeah, let's try this. Num oscillators. Just going to set this to 1. I'm going to get rid of this line. And this. Let's just make sure this is all correct. So we're going for each of the oscillators, setting its frequency, updating the LFO. I have a feeling this might be incorrect because We don't have an LFO per oscillator, we have an LFO per... We have one LFO shared for all oscillators, so this is actually getting updated 4 times too quickly. Now rethink LFO, this gets updated 4x too fast. We'll handle that another time. So I'm going to get rid of all this where we were changing the base frequency per shape. So they all have the same. Again, this amplitude, I'm not going to do this odd harmonic stuff. So let's only do sawtooth. See how that works. Doesn't work at all. Doesn't work at all. How come? Sawtooth ask. Set this to 2 oscillators, then what? I should still work with 1 oscillator. Phase DT, we're doing phase. Sawtooth. Ah, we forgot to actually return the sample. We did that for square wave. All right. And let's try this test where we do like a really low sample rate. My worry is I think this was expecting t to be between 0 and pi. Although it looks like it shouldn't matter, it's invariant because it's only handling with dt. And let's try square wave. So we're going to set u to 0 and square wave to 1. So yeah, we're getting those steps. Alright, I had to go off camera for a minute, but I'm back. And while I was gone, I think I know where I was going wrong. So I'm going to set the sample rate back to 8000, just so it makes the aliasing effect a little simpler to do. So if we come down to our square wave, I've commented out our adding in the band limited ripples. I think we've got this inverted. So we're setting a 1 if our phase is above 0.5 and negative 1. So I'm going to flip this around to less than. So if our phase is less than 0.5, we output positive 1, otherwise we output negative 1. And let's enable this. Well, let me showcase. So I'm going to disable, well, I'm going to let this square wave alias. I'm not going to add these band limited ripples. So notice I've also added the fundamental frequency up here, and as we get higher and higher, it starts to sound a little weird. So let's go to 1205. Let's come to Audacity. Oh, looks like it's changed that. And record this. And then, so we can see the square wave. Oh, it's very, let me amplify that by, I don't know, 20. So here's our square wave. I'm going to analyze it. So you can see all these various frequencies that are in that square wave. So now let's enable add in these band limited ripples. Notice it sounds a lot nicer towards the high frequencies. And let's record that. Let's close this out and let's analyze this. And look at that. Look how much cleaner our frequency spectrum is now. We've got a fundamental, 1370, yep, that maps up to what was showing in the corner, and just a few overtones. So that's what band limiting does to our signals. Let's see if it's the same for our sawtooth. So I'm going to set the square wave amplitude to 0 and the sawtooth to 1. Just gonna make this a little bit more louder. And now let's go to our sawtooth wave. If we comment this out, see how much muddier that sounds, and even the shape is different if you look on screen. We're going to band limit it. Look how much nicer that is. So we can cross this off. We've done band limited waveforms. So I think in the next episode, episode 5, I am going to start adding in a graphical user interface to be able to tweak all these things. And we're getting close to actually making a tweakable synthesizer. So I'll see you next time.